Hey everyone, so today we will be proving proof 2, which is that if functions f and function g are integrable over the closed interval a to b, then f plus g is also integrable over the closed interval ab. Moreover, we can also say that the integral of f plus g is equal to the sum of the integral of f and the integral of g. And so I'm going to go ahead and write this out just to make it easier to show. So if f and g are integrable on closed interval a to b, then f plus g is integrable on closed interval a to b. And then likewise, we can say that the integral of f plus g is equal to the sum of the integral of f plus the integral of g here. And so this is what we want to prove. So in order to jump into the proof now, we can now first look at the subinterval S of some particular partition of P. And so what that looks like is that for any subinterval S on some P. And so likewise, we want to define S as the closed interval of some t k minus 1 to some t here. And so now we can say that for all elements in this subinterval, we can say that the function value f for input values of x in this subinterval S, we can say that they're greater than or equal to the infinitum of the function f over the subinterval S. And so this m of f of s simply is just the infinitum of the function f over s. And so likewise, we can say the same for function g. So we can say that for all x in subinterval S, we can say that g of x is greater than or equal to the infinitum of g over s. And then now that we have these two inequalities, we can then manipulate inequalities and sums in order to get a particular result that we want. So in this case here, what we can do is that we can simply add these two different inequalities here. And so what we get now is we get something that resembles for all x in subinterval S, we have f of x plus g of x is greater than or equal to the sum of the infinitum of m of f over s plus the infinitum of g over s. And so because we're talking about the sum of the function of f over f of x and g of x, we can say that this is also true for the sum of all values of x and s as well. So then we can say that for f of plus g of x, we can say that this is also greater than or equal to the infinitum of f over s plus the infinitum of g over s here. Okay. And so finally, what we can now say is for this left-hand side, because we know that all function values on this left-hand side here is greater than or equal to the infinitum of f over s and the infinitum of g over s. We can also say that the infinitum of f plus g over s is greater than or equal to f over s plus the infinitum of g over s. And the reason for that is because if there is some function value of f plus g that is less than the sum here, less than the sum of the infinitum of f over s and the infinitum of g over s, that means that the infinitum of f plus g would be less than that sum, which is not true in this case. So that's why we can assert that the infinitum of f plus g over s is greater than or equal to the sum that's on the right-hand side here. And so that completes the first setup for this inequality here. The next step now is to then multiply both sides of these equations by the length of s. And before, we define the subinterval s to be the closed interval from t sub k of -1 to t of k here. And so when we multiply both sides, we get the infinitum of f plus g of s times the interval. So in this case, the interval here could be defined as delta t is equal to t of k -1 minus t of k. And so we can simply say that the infinitum of f plus g over s times delta t is greater than or equal to the infinitum of f over s times delta t plus the infinitum of g over s times delta t here. And now that we have this setup here, we can now sum over the interval s over the partition P. And so what that means is that we can now leverage the definition of the lower Darboux sum here that we've talked about, since we have the infinitum and we also have the interval, the length of s itself. And so what we get now is that for this value here, we can now say that this is the lower Darboux sum of f plus g over the partition P. And we can also say for this right-hand side as well, greater than or equal to the lower Darboux sum of f over P plus the lower Darboux sum of g over P as well. And so this defines, so going from the previous step to the next step, we are simply just defining how the lower Darboux sum is when we have like these infinitives times the interval size of s here. And so now that we have that, we can also similarly say this for the upper Darboux sum as well. And this would resolve around the same argument. Notice here that these sums here are kind of an underestimate of the lower Darboux sum here. So in a very similar argument, we can say the same for the so kind of a mirrored argument. So we can say that for the upper Darboux sum f plus g of p, we can say that this is less than or equal to the upper Darboux sum of f over p plus the upper Darboux sum of g over p. And this is essentially the same as saying that the sum of these upper Darboux sums overestimates the upper Darboux sum of f plus g. And so now that we have these two here, we can now say that for any function, and for any function, once we fix the partition P, we can automatically say that the lower Darboux sum is less than or equal to the upper Darboux sum. And this is true because the lower Darboux sum, remember that it's made up of the infinitum, and the upper Darboux sum, that it's made of the supremum. And we know that the infinitum is always less than or equal to the supremum when we have any function and we fix some particular partition P. So then, leveraging like this knowledge here, we can immediately say now that the lower Darboux sum of f plus g, of f plus g over p is less than or equal to the upper Darboux sum of f plus g over p. And given the two inequalities that we have here as well, we can also say here that this quantity here in the middle, we can say that this inequality in the middle is greater than or equal to the sum of the lower Darboux sum of f over p plus the lower Darboux sum of g over p. And then likewise, we can say that the middle term, the middle quantities, are less than or equal to the upper Darboux sums of f over p plus the upper Darboux sums of g over p. And we can say that this is true for all partitions here. Now that we have that, we'll later leverage this inequality here for when we're trying to show that f plus g is integrable over a to b. But for now, let's put this to the side for now and move on to the next step of the proof, which is now to leverage the definitions that we now know for, or is to leverage what we know about the functions f and g, which in this case, we know that they're both integrable on the closed interval ab. And so we can now use an epsilon type argument for these individual functions here. So now we can say that for any epsilon greater than 0, we can say that since f is integrable, we can say that there exists some partition, P1, such that the difference between the upper Darboux sum of function f of P1 minus, no, the difference between the upper Darboux sum of f over p and the lower Darboux sum of f over P1 is less than epsilon over 2. And so this argument can also be said for g as well, because we know that's integrable over the closed interval ab. So we're going to say that if g is integrable, we can say that there exists some partition, P2, such that the difference between the upper Darboux sum, g of P2, and the lower Darboux sum of g over P2 is less than or equal, or is less than epsilon over 2 here. And so now that once we have these two different inequalities here, we can now take the union. So we can take the union of these partitions to form P. So then this can be represented as P is equal to P1 union P2. And what this means, like for the purposes of our proof, is that we are essentially unioning the breakpoints for P1 and the breakpoints from P2, so that we end up with a finite partition that is represented by the partition P here in this case. And so because we now have a finite partition, that means that for a finite partition, we can say now that for this finite partition, that the upper sum, so the upper sum, you can think of the, remember that the upper sum is an overestimate of the I would say the actual integral or the actual sum here. So then because we have a finite partition, this upper sum now decreases. And likewise, we can say that the lower sum now increases here. And so now that we have this new partition P here, we can now say that the difference between the upper Darboux sum of f over p and the lower Darboux sum of f over p is less than epsilon over 2. And likewise, we can say that the difference between the upper Darboux sum and the lower Darboux sum of g, so upper Darboux over p, minus the lower Darboux sum, or lower Darboux sum g over p, is less than epsilon over 2 here. Okay. And so now that we have these two inequalities, once we put them together, what we get is the upper Darboux sum of f over p, partition p, plus the upper Darboux sum of g over p, minus the lower Darboux sum of f over p, minus the lower Darboux sum of g over p is less than epsilon here. Okay, so now that we have that, we can go back to our previous inequality that we had here. So let me go ahead and copy that. Paste it here. Okay, Based on what we know about these inequalities, given that they are less than, for some epsilon greater than 0, we know that the difference between this and this here is now less than epsilon. So what that means now is that this term in the middle here would now be squeezed between this epsilon as well. And so given that these values are kind of squeezed together, we can almost kind of say now, or we can definitively say now that like these two inequalities on the side here, on the left-hand side and the right-hand side are less than epsilon, we can also say that the inequality in the middle is also, or the difference between the two quantities in the middle are also less than epsilon. So now we can assert, based on this kind of squeeze type through this proof, that the upper Darboux sum of f plus g over p minus the lower Darboux sum of f plus g over p is less than epsilon. And so because this is true for some value of epsilon as well, that's greater than 0, we can now say, or we can now assert that f plus g is integrable over the closed interval AB. And so that completes the first step of the proof. But now we have to prove the second part of the proof, which is to say that the integral of f plus g is equal to the integral of f plus the integral of g here. And so to say that, what we now know is, because since we know that f plus g, the integral of f plus g is integrable, we can now say that, oops, let me go to the next page. Okay, we can now say that the integral of f plus g, it takes on values that are either less than or equal to the upper Darboux sum of f plus g over the partition P, and it's greater than or equal to the lower Darboux sum of f plus g over this P here. And so based on the squeeze argument that we had up there as well, this sort of, okay, so based on the same squeeze argument that we had up here, we can now say that these values are greater than or equal to the lower Darboux sum of f over partition P plus the lower Darboux sum of g over P. And likewise, we can say here that the upper Darboux sum of f over P plus the upper Darboux sum of g over P. And so we now know that this inequality is true based on the inequalities that we defined earlier up above in this question here, or in this proof here. And so likewise, we also know that the integral of f and the integral of g are also squeezed between these two lower and upper Darboux sums here as well. And so because we can make the difference between the left-hand side and the right-hand side be less than epsilon for some epsilon greater than 0, we can say that both the integral of f plus g and the integral of f and plus slash the integral of g are squeezed. And so we can ultimately now conclude that the integral of f plus g is equal to the integral of f plus the integral of g, which completes our proof. Okay. And I think that should be it.